state of the map and to the academic track / OSM science meeting, which happens within State of the Map. I'm Eric Grünberger. I'm the co-chair of the scientific committee of the academic track. I'll speak more about the academic track later on, because we're already running. But before I'll introduce our first speaker, I'll just say that I'll be collecting first questions via Venuless to give fair chance to people that are joining remotely to ask questions. And so you're welcome to post your questions on Venuless, and afterwards we'll also collect questions from the audience if time would allow. And now we'll move on to our first speaker, which is Anna from the Alan Turing Institute, together with colleagues from HOT. And she's going to tell us about their new tool for AI-assisted mapping, and basically on their checking how well it works, I guess. Yeah, go ahead.
Thank you. Thank you, good morning, everyone, and thank you for managing to come here despite the social yesterday. I'm going to talk about my research on assessing the performance of FAIR, or in short, mapping building footprints with FAIR. Starting from a little introduction, I'm originally from Italy, and I'm now based at the Alan Turing Institute. And as a Turing Research Fellow, I am seconded at HOT, the Humanitarian OpenStreetMap Team. HOT developed through the tech team, and in particular through Omran and Kshitij, which are the product owner and the backend developer. They developed FAIR. FAIR, this is the website. It's an OpenAI-assisted mapping service, where F stands for free and open source, AI stands for artificial intelligence, R stands for responsible mapping. And what it does, it allows you to to fine-tune a pre-trained model of machine learning for computer vision, and you can then eventually import the features, these building footprints, just to make sure is the buildings outlines to OSM eventually. This is a really simple diagram to explain how computer vision and machine learning works, specifically in FAIR. So we start from labels for the buildings, where we know that the buildings are, and we have the ground truth image, which is an RGB image, and it's going to be, I don't have the pointer, but yeah, it's transformed to the mask, which is a binary mask, where you have buildings and non-buildings, basically, and so it's in the same raster format of the RGB image, basically. Then they go through the machine learning model, where the training happens on a set of imagery, and the validation as well. So the accuracy happens on the validation. This generates a set of checkpoints, also, or weights. And with these checkpoints, you can run the prediction on other imagery. Yeah, you can do this on different, for each different city with FAIR. So this is a general functioning of computer vision for image segmentation. But in particular, I'm going to show you the dataset that FAIR uses. So the RGB comes from OpenAreaMap, which is also an open service that provides access, and you can upload your own drone imagery or other unmanned aerial vehicle imagery. And it has mainly centimeter resolution, so it's very useful. And the labels you generate through the FAIR website. You create your own training data set. This is one that I generate in Russia. You upload your OpenAI imagery, and what you do, you create areas of interest where you can check. Yeah, there are different buttons, but you fetch the data from OpenStreetMap. You check if it aligns with the RGB image, and if not, you map it yourself through either JOSM or ID, and it goes straight to OpenStreetMap. So you do, I think it's very convenient, because in the same time you map where there is nothing mapped already. So okay, then the pre-processing to the binary masks happen also in FAIR, in the FAIR website, and it generates tiles 256 by 256. I'm gonna tell more about this. So the machine learning engine behind the FAIR is called RAMP, which stands for Replicable AI for Microplanning. It was developed, was chosen by HOT in a series of initiative. This was created by the WHO, the World Health Organization. And the backbone CNN convolutional network, neural network model of FAIR is this FUNet model, where you have a efficient net as a decoder and an UNet as a, encoder and decoder. That's a classical CNN backbone structure. Anyways, without going too much specific, this comes from a paper from by Haiti in 2020. So going now more to my research, to the parts of the research, I'm going to explain to you the reason why this just started. So once you train your stuff in your training data set on FAIR, you can get an image like that. This is from Pemba. When you run the prediction, you can see that some of the buildings are not mapped. You can tweak a bit the confidence or tolerance, other parameters that you can tweak, but sometimes it doesn't manage to detect buildings anyway. In other areas, this is an image in Bogota, in Colombia. It detects them much better, and I didn't even need to tweak the parameters. So I came up with a question on how accurate is FAIR in detecting buildings in different conditions. Does it perform better in some areas of the world other than others, or does vegetation around affect? I mean, so yeah, I went to analyze this basically. And when we speak about accuracy, at the moment RAMP uses the categorical accuracy as a metric. So on the left side, you have the buildings which should be detected, and this is the building which has been detected. So accuracy in RAMP stands for the true positive, whatever is correct, correctly detected, on top of all the possible samples. And I've added 4 other metrics after review. Initially, I wanted to find myself the best metrics. Then I found this very good review, which says that the best metrics would be intersection over union, IOU, which is a measure of the overlap of the predicted building on top of the actual building. And other 3 very common metrics which are used are precision, which is the true positive on top of what is predicted positive, and the recall or sensitivity, which is the true positive on top of what should have been predicted. So then going to the dataset now, I've generated a dataset taking 25 urban regions, which are spread in 21 countries, 3 different zoom levels, which are available in FAIR, and generated 8,400 images, 256 by 256, in average 350 per region, more or less, and the resolution is centimetric, as I said before. So the location of the image, the urban regions is this, and then wanting to find variables on which to categorize the different possible cities, I have come up with 3 variables. The first one, I call it degree of urbanity. I'm going to show you some examples. We pass from rural areas, like this is an RGB plus the binary mask adjacent to it in Indonesia. So we have rural, peri-urban, this is a neighborhood in Kampala, in Uganda, urban, the image from before, and the refugee camp is a category on its own because it's special. Second variable, I chose the roof cover type. So we have shingles, metal, usually are tins roof, cement, and mix. It's either a mix of the above or other categories which were not covered by the above. Then probably the most important, urban density. So we can have really dense cities like this, where you have buildings connect one to each other, like in Montevideo. Sparse, this is a rural area in Croatia. And then I've created this grid category, which is something in the middle, which is kind of sparse, but at the same time, you have a special pattern which is repeated. So going to the results now, I run the training on all the 25 urban regions for 20 epochs, which is what the RAMP uses usually, and at 4 different batch sizes, which is also another variable which could be relevant for the analysis. And the accuracy metrics are the 5 metrics I explained before. So categorical accuracy, precision, recall, F1 score. I didn't mention before, F1 score is the harmonic mean between precision and recall, and the intersection over union. And they're commonly used for, it's okay, for image segmentation analysis. So when you run the training, you can get to a graph like this. So basically, you have the 20 epochs on X, and what the model does, it tries to minimize the loss. So the loss, you have a training validation track here. The loss goes down. This is an ideal case, and where the loss is reduced to the minimum. I start from 1.2, it goes to almost 0. And the accuracy, it's on the right x-axis, is from 0 to 100 or 1. So I'm plotting here the value for all the metrics, for all the five metrics. And what RAMP does at the moment, what FAIR does, it says for the checkpoints, which I mentioned before, it has early stopping in place, which means that it takes the highest value of accuracy for the categorical accuracy, and then it saves the checkpoint at that point, and then it does prediction with the model at that point in time, basically. So my question was, what happens to the other metrics when the categorical accuracy is at its highest? So, I mean, how do the IOU perform, for example, which is supposed to be the metrics which is suggested for this type of analysis? So I took the values of all the other metrics when accuracy was the highest, and I plotted it in a plot similar to this one. Okay, so in this plot, for each row, we have the urban region, and on X, we have the 5 metrics, and also the 4 batch sizes, and they are grouped by the variable density. So we have dense, grid, and sparse. And I discarded the other 2 variables, urbanity and roof type, because they were not showing such a good trend. I mean, what we see here is, I think clearly it's a pattern going from bottom to top and from right to left, with the recall and IUU performing worse, basically. Which means, while precision is higher, so it means that the model detects that doesn't detect all of the buildings, but the one that detects, it does it precisely, like, so yeah, then, so I concentrated more on density, and I plotted it again for all the metrics together. And we have, again, dense, grid, and sparse cities. And I've discarded also the batch size, because, I mean, the pattern was different, but it was consistent among all the different batch sizes. So, in conclusion, the density seems to be the major drive in affecting the performance. And in particular, when one uses FAIR, needs to know that the dense areas perform in average for accuracy 4.8 and 4.2% less than grid areas or sparse areas. And when considering the intersection over union alone, this goes up to almost 8% in difference of performance. So it could be interesting to see the 2 cases where the performance is the worst. And this is a zoom into an area in this city in Indonesia. So probably what happened here, it was, you see the houses here in the north seem quite flat. There doesn't seem to be shade, or if there is shade, it's on 2 sides. So maybe there was some post-processing effect on the image after the acquisition. Though the model seems to learn, but slowly, so maybe with a higher number of epochs could have been a better result. And in this case, in Bangladesh, I mean, where it's difficult for the human eyes to identify, it's also difficult for the computer, basically. So we can see here there are many buildings with vegetation on top, and over here there are fences but no buildings inside. And the model does this weird behavior where the loss grows and then goes down. So maybe also here having a higher number of epochs would help. But again, it's a really dense area, so the performance is going worse. For the future, FAIR is concentrating on using other models rather than RAMP to test if they have different performance. Specifically, they are testing now YOLO version 8. And they would like also to detect other features like ponds or vegetation land cover features. That's it. Thank you.
So thank you, Anna.
We have time, yeah.
We have some time for questions, actually. I don't see anything in the venue list, so I ask anyone who's interested of asking a question to come up so everyone can hear. So just, you can line up if you want, one by one.
So thank you, Anna, for the presentation. So I have two questions, but I will start with only one, and if there is more time at the end, I will ask the other question. I'm curious if I can use now your model into cities that was not part of the training model for, like, I don't know, England or other countries that was not in the first place in the model.
Yeah. Yeah, of course. Maybe I wasn't clear, but if you have a drone imagery, you can, if you are happy to upload it openly and have it openly accessible, it can go up onto Open Area Map, and then when it's an Open Area Map, you can import it to FAIR. Otherwise, if you want to use it on specific areas, I mean, you can just speak with the developers, and they can also put it available for you privately. I mean, but yeah, this is another path. But in general, you can try to go to Open Area Map and see what is available there. And use it. It's not map. There are no imagery everywhere with the same. Like in England, there is not many, for example, at all. But yeah, you would like something that covers as much of the city as possible. Yeah. Please.
Thank you so much, Hanya. I have two questions also, and I'm just going to go ahead and ask both of them.
Yeah.
First, it's interesting that I wasn't familiar with your techniques for the different kinds of accuracy evaluation, and I noticed that the IOU is reliably lower than the other indicators. Is that to be expected in this kind of evaluation, or does that tell us something interesting about the results, and if so, what? Second question, what's next? What are you excited about in the future?
Okay. So it seems like low IOU is consistent with the difficulty of the model in distinguishing the feature building from the background. So it is consistent with the high density, I would say. The future, I mean, let's see what I'm going with the hot for a full year. Let's see what's next with them. But again, probably we're gonna test the YOLO V8 performance as well. Yeah, there is other things in the drawer, but we'll see.
There are two questions from Vanillas, so I'll ask them both. First, have you compared the quality of the model to human mapping in these areas? And second, that's the tricky one, is it ethical to use AI mapping in areas where your research shows that it doesn't perform well?
Yeah, okay, good. Nice. I start from the second because I remember better. They're actually connected somehow. Because yeah, I didn't have. If Omran would be here, would explain more about hot philosophy behind it. But these things are not going to be mapped straight to OpenStreetMap. There is always a component where you actually have to accept the buildings or not. And yeah, the question is how fast it is to map humanly with human beings, or how much is fast to map with AI. And yeah, we didn't calculate that, but yeah, in general, you would think that it accelerates the performance very much.
It's about if you just let humans, would the quality be better than relying on AI?
Yeah, we do use humans anyway, because I mean, if the quality is not good, the building is not going to be uploaded. So of course, the human can be better than the AI. I mean, my honest opinion is that it's better. Yeah.
Okay. We have time for one more quick question. Yeah.
I didn't say, but there's going to be a second part because it's still in development, and I'm more concentrating on the research part. But they want to go on the field to also check the results. It's part of the process. Yeah.
Thank you once again for your great presentation. So I just have a question, whether you done some classification, whether if it is like houses, multiple family buildings or sheds or something like that, because in the future probably it will be really hard to distinguish from the area limiters. So did you maybe have some analysis on that?
What do you think is going to be harder?
Yeah, it will be hard actually to recognize whether something is like just rooftop of I don't know, some balcony or something like that, or it is like just a real building.
Okay. So the question is, it's going to be harder, and if we are able to detect the levels of the building.
No. Have you done any detections classification of that? So whether it is like a building like this one, or it is like home?
No, the type of building. No, it's not been done. And yeah, but actually, I think it's worth to say that because you fine-tune the model on your own city, so you should learn from the specific city different features. So, for example, if you wanted to learn more of a certain type of building, maybe you can change just that type of building. So maybe that could be useful, but you can't have it done by the AI. You need to do it a priori. You know what to train it on. That's what I think could be done. Yeah, you're welcome.
Thank you very much, Anna.
Yeah, welcome.